Today we're talking about Lorentz transformations. So far we've talked a lot about times and positions observed by different observers. So the scenario that we often talked about was somebody stands on the ground and there's a train that's moving with respect to this observer, and there's another observer on the train. And then these observers measure various times, various distances. They look at different clocks. And we had three fundamental effects: the loss of simultaneity, which appeared in this so-called rear clock ahead effect. We talked about time dilation, the rates at which clocks tick according to different observers can be different, and also length contraction. So the Lorentz transformation is essentially putting all of that together. So the general scenario that it describes is, again, we have two reference frames. So maybe reference frame S and some reference frame, let's say S prime, that's moving with respect to S with velocity V. So S prime can be the train, and S can be ground, someone standing on the ground. And S prime is an observer on board the train that's conducting some experiments on the train. So we can have different events. Something that happens has a specific time and position in either reference frame. And in particular, we're going to consider two events. So there's an event one that happens at some position and time, and then another event two. Maybe somebody claps their hands somewhere, or there's a paint bomb that explodes, or something like that. So then the difference between times and positions of these events can be written as delta x and delta t. So let's say in frame S, we have delta x and delta t. In S, rather. And in S prime, we have delta x prime and delta t prime. So these are the times and distances between two events that observers standing on the ground and standing on the train measure, respectively. Lorentz transformation essentially gives us a relationship between these. And as you can imagine, the fundamental effects that we talked about should all be encoded in these Lorentz transformations. So let's start with a setup. Let's go back to the picture of having someone standing on the ground here. Person, and there's a train here moving with velocity v. So we want to consider like two different events. So let's go to the example of paint bombs. So event one is a paint bomb on the left-hand side of the train explodes, and it at the same time leaves a mark on the ground and on the train. Event two is another paint bomb in the front on the right-hand side explodes and leaves a mark both on the train and on the ground. So we have this scenario. This happens first, and then there's a mark already here, and then this happens. So in the frame attached to the train, what we see is the train is at the same position. So let me move this to be just below. So that's in the frame that's attached to the train. And then the same thing on the ground. The ground is over here. The ground is moving with velocity v to the left in this frame, right? So let's say that's the ground here. That's like a platform. And it's moving this way. Let me just fit it, draw it over here. So that's my platform. And it's moving that way. And when that happens, there's going to be a mark on the ground. So because it's moving this way, when the second paint bomb explodes, the ground is somewhere over here, or that particular platform that we're staring at is going to be somewhere here, still moving with velocity v. So the situation in the train's frame. Okay, so an observer on the train sees a spatial separation to be like just the length of this train. According to her, let's call that xt, and a time t train that has passed. Right, so time tt on train. Okay. So then this observer, if she looks at what's happened on the ground, where are the marks on the ground, what is she going to see? Well, she sees a distance xt from here to here. And then she sees that this end of the platform has moved by a distance v times tt, right? That's the time that has passed. And according to this observer, the ground has been moving with constant velocity v. So that's the situation. That's what an observer on the train observes. So the distance between the two marks on the ground, according to the observer on the train, is going to be xt plus vtt. So let me write that in words. It's kind of important here. Let's do that. So distance between two marks on the ground, according to the observer, on the train, is xt plus vtt. Okay. Now we can ask ourselves, what is that distance between the two marks according to an observer on the ground? And we know there has to be length contraction, right? So the observer on the ground measures a longer length, right? So the proper length in the ground frame that's not moving with respect to that length must be larger. So when it's contracted down by a gamma factor, according to the observer on the train, it leads to xt plus vtt, right? So this is, again, a length on the ground that the observer on the train measures, right? So the proper length, the corresponding length in the frame of the ground must be larger, so that when it's divided by gamma, it leads to this quantity. Therefore, the same length between two marks on the ground must be gamma times xt plus v tt, because then Lorentz contraction says if that's the proper length, the length the observer on the train measures is that thing divided by gamma, which gives me xt plus tt. So that's going to be like the distance on the ground according to an observer on the ground. Let's call that xg. So xg becomes, again, gamma xt plus v tt. So that's essentially one of the equations of the Lorentz transformation. It gives us the spatial distance in frame S in terms of the spatial and temporal distances in frame S prime that's moving with the train. Now, let's see what we can say about the time between these paint bomb explosions according to the person on the ground. Okay, so now let's draw the same situation, but now instead of in the frame of the train, which we did here, so we drew the situation in train's frame. So the same scenario, but let's do that now, the situation in the ground's frame. So here the platform is there, it's not moving. Then we have a train. We have this paint bomb exploding, leaving a mark here. And then the train is moving to the right. So then it's going to be over here when the second paint bomb goes off. Okay. So that's the situation on the ground. So let's think about what the clocks on the train read when these things happen. So without loss of generality, let's say at this point, the clock on the train reads 0. And then we know that according to an observer on the train, of course, there's going to be synchronized clocks everywhere inside that frame. But we're looking at this in the ground frame, so there's no simultaneity. So the clock over here, according to an observer on the ground at that point in time, will read minus xdv over c squared. Right, so that's what we calculated for the rear clock ahead effect. So if the rear clock reads 0, the clock in the front of the train must be behind by the amount equal to the proper length, the distance measured on the train's frame times the velocity divided by c squared. So at that moment, that's what the observer on the ground sees. Now, when the second paint bomb explodes, the front clock here must read tt, right? So if this clock over here, if this clock at this event reads minus xdv over c squared, and the same clock, that's the clock in the front, reads tt, Time on that clock has advanced by tt plus xt v over c squared. So by, let's say, this amount, and the reading, like the change in the reading of a clock is really the proper time, right? It's the time in that reference frame. So then the time on the ground must be larger by a factor of gamma because of time dilation. So then time dilation says Tg is gamma times that quantity. That's the second Lorentz transformation. So let's write it in a nicer notation, maybe. So see, we had two events, the explosion of those two paint bombs, and we calculated the time and distance difference between those two events in two reference frames. So another way to write the same thing would be to write delta x, that's spatial separation in the S frame, in the frame outside the train, in the ground frame, to be equal to gamma delta x prime plus v delta t prime. That's essentially this equation over here, right? So I'm just replacing xg by delta x and xt by delta x prime, tt by delta t prime. And this equation I can replace with delta t, time interval in the frame attached to the ground is going to be gamma delta t prime plus v delta x prime over c squared. So these are the Lorentz transformations. They relate the times and distances between two events as measured from two or by two different observers that are in two different reference frames. So this equation looks kind of nicer if instead of t, I use ct. So the transformation becomes more symmetric. So let's drop the delta. But just for simplicity, we know that these are time intervals. So sort of the origin is set to 0 for both frames. So what we know is x is going to be gamma x prime plus beta ct prime, where beta is just v over c. And then ct, so I take the other equation just multiplied by c, is going to be gamma ct prime plus beta x prime. It becomes a symmetric equation between these. And again, it's kind of nice to also write this in a matrix form. I write gamma here, beta gamma, gamma, x prime, ct prime. Gamma, again, was this factor that's ubiquitous in relativity. Also, with that definition of beta, it's going to be 1 over square root of 1 minus beta squared. So the Lorentz transformation, essentially we derived it by kind of considering a scenario making use of the various fundamental effects, time dilation, length contraction, and the rear clock ahead effect, we can kind of more directly also get the Lorentz transformation from these effects. And of course, these effects then are special cases of Lorentz transformation. So let's start with an alternative derivation. Maybe makes that connection even more clear. So generally, we expect a linear transformation. So we expect in general something like delta x is a delta x prime plus b delta t prime. And delta t is c delta t prime plus d delta x prime. So the reason for this is where a, b, c, and d are just constants that can only depend on velocity. So why do we expect that? Well, first, there is no special time and place in an inertial reference frame. All times are kind of equivalent, or positions in space should be equivalent. So if A, B, C, or D depend on where it is in that frame or what time it is, they would be picking some special time and places, which doesn't make sense. And then the reason we expect a linear transformation is that, we should agree on lack of acceleration, for example. So if an object is moving at constant velocity, let's say in the S prime frame, so delta x prime is some velocity times delta t prime, we expect that object, which can itself form an inertial frame, to be moving at constant velocity also in S. So that means delta x over delta t must also be a constant. So we cannot get like different powers of delta x of positions than power 1. And then there are other considerations, like this has to reduce the Galilean transformation in the limit of small velocities. So we're going to work with that form, which we expect on general grounds. And then let's see what we can learn from the various fundamental effects. So think about time dilation. So time dilation has to do with the proper time of a clock. So let's say that clock is in the S prime frame. It means for 2 events, maybe 2 clicks of that clock, delta x prime is 0, right? They happen at the same position in the reference frame attached to the clock. And then what does time dilation say? It says the proper time is the shortest time. So delta t prime is going to be the proper time. It's in the frame where there is no displacement. So gamma times that is delta t, the time interval in this other frame in which the clock is not stationary. Okay, so that's one special case. So going back to our equation, what do we see? So if delta x prime is 0, and then I have a relationship between delta t and delta t prime, that means delta t is c delta t prime. Here I have delta t is gamma delta t prime. So that means c is equal to gamma in that transformation. Note that I could have switched the the primes and the unprimes. So for example, if I pick delta x equals 0, that means I put the clock in reference frame S. So then delta x equal to 0 means that reference frame S is attached to the clock. And then delta t would be the proper time. So then it means delta t prime is gamma delta t. It just switches also the primes in these equations. So we just pick one set that's kind of more convenient to get like those parameters in the transformation directly. Let's now look at length contraction. So again, you can imagine some time difference should be 0, right? When you measure the length of something, you measure the position of its two ends at the same time. So let's say I use, again, delta t prime to be equal to 0. So that gives me like delta x prime is equal to delta x over gamma, right? So I'm imagining delta x to be the proper length of an object that's in frame, that's stationary, let's say, in frame S. It's moving with respect to S prime. And in S prime, I want to look at its length. So I have to look at two events at its two endpoints at the same time in S prime. And then delta x prime would be the length that I measure in that process. And that will be contracted by a factor of gamma. So what does that tell me? So I have a relationship between x prime and x and t prime is 0. So going back to this equation, yeah, it seems it should be saying something about a here, right? So x is ax prime when t prime is 0. So a must be, again, gamma, because delta x is a times delta x from here is gamma times delta x prime. So a is also equal to gamma. Okay. Now I can consider like the relative velocity of the two frames here. So let's see, let's draw a figure just to see what we're doing here. So imagine, this is the frame S, this is S prime. In S, we see S prime moving this way. Then imagine two events happening at the same position, let's say in S, so they have delta x is 0. So now, looking at those two events, from the point of view of S prime, what we'll see is, well, I will see now S prime is stationary, and then S is moving this way with velocity v. So maybe the first event happens here, and then if a time delta t prime passes, according to the observer in S prime, the next event will be somewhere over here. That's a travel distance of v delta t prime to the left. So from here, we say if delta x is 0, we expect delta x prime to be minus v delta t prime. So now that's a relationship where delta x is 0, x prime and t prime are related. So going back here, if x is 0, x prime and t prime are related, that says something about the first equation, right? So let's say a delta x prime plus b delta t prime must be 0. So comparing this and that tells me that in this case, I guess V is B over A. So B becomes gamma because A was gamma. So B is gamma V. And finally, we can look at the rear clock ahead effect. So let's see. So let's consider a situation where delta t is 0. Again, drawing the pictures that we see. So here we have S here, and this is S prime moving with velocity V. We're saying the rear clock is ahead. So delta t is 0 because the observer in S is looking at the two clocks in the front and back at the same time in the S reference frame. So the rear ahead, so let's say that's 0. So the front must be behind, and that's behind by minus V, that separation, which is in the primed frame, in the frame moving with the train over C squared. So, and that's reading on the clocks inside S prime. So that's like a delta T prime. That's the time difference according to an observer on S prime, right? They have clocks that are synchronized throughout that inertial frame. So delta T prime will be minus, right? The front, if delta X prime is positive, front is here, is ahead, and then it's running behind. So that's going to be minus V delta X prime over C squared. So now I have a condition where delta T is 0, and I have a relationship between X prime and T prime. So going back here, yeah, that should give me the ratio of C and D essentially. So I have C, this is capital C, delta T prime plus D delta X prime is 0. So that means that this thing must be D over C. So D over capital C. I'm not sure. Let me make it like that. So it's clear that it's not the speed of light. It's that coefficient in the transformation. That's equal to, bringing that to the other side, that should be V over C squared. And C we already calculated was gamma, so D must be gamma V C squared. So essentially, like that, we see that these fundamental effects are special cases of the Lorentz transformation, and then kind of demanding that the transformation is linear. Essentially, these special cases are enough to determine the entire transformation. So there's the same amount of information in the fundamental effects and in the Lorentz transformation. All right, so let's work out a quick example to just see how powerful the Lorentz transformations are. So this says, we have a train of proper length L moving with speed, let's say 5c/13, so really, really fast train. with respect to the ground. And the ball is thrown from the back to the front. And it has, let's say, speed c/3 relative to train. So we want to know how long the ball is traveling and how far does it move. According to someone on the ground. All right, so that's pretty straightforward. So essentially, we know what's happening on the frame of the train. It has a proper length L. We know that the speed is c/3. So we know the time should be just L divided by c/3. So we know sort of delta x prime is just L. The ball moves from the back to the front. Delta t prime is going to be L over c/3, which is 3L over 3. Let's find gamma, 1 over square root of beta squared, which is v over c squared, and that v over c is 5 over 13. So that gives me 1 minus 25 over 169. 169 minus 25 is 144, so that's 12 squared. So this thing becomes 13 over 12. And then we just plug that into the Lorentz transformation. So how far does the ball travel according to someone on the ground? The ball leaving the back of the train is the first event. The ball hitting the front of the train is the second event. The spatial separation between those two events is delta x prime on the frame of the train. The temporal separation between those two events is delta t prime in the frame of the train. And then the spatial separation between the same events in the frame of the ground is going to be delta x is gamma delta x prime plus v delta t prime, right? So we can just plug that in. 13 over 12 L plus 3L over 3, sorry, 3L over C, that's my delta t prime, and V, the velocity of the train was 5C over 13, 5C over 13. So what does that become? So the C's go away. 3 times 5 is 15 over 13. 15 then plus 13 is going to be 28. Then the 13 cancels out, so it's going to be 28 over 12L. And then they're divisible by 4, so that becomes 7L over 3. Okay, so we find delta x. Similarly, to find how long has passed between those two same events in the frame attached to the ground, we can use the other Lorentz transformation. So let's say delta t is gamma delta t prime plus v delta x prime over c squared. So 13 over 12. Delta T is 3L over C. Sorry, delta T prime rather. Then plus V is again 5C over 13. And then delta X prime is L over C squared. So this reduces to something, 11/3 of L over C. Something like that. So that's kind of a nice, simple example of using the Lorentz transformation. All right, so a simple consequence of Lorentz transformation is a very quick derivation of the velocity addition formula. So velocity addition from Lorentz. All right, so the situation is, again, we have some frame S prime that's maybe moving with velocity v2, and we have an object that has velocity v1 with respect to S prime. And then we're interested in the velocity of this object in reference frame S, in which S prime itself is moving with velocity v2. Okay, so let's take, again, two events, maybe this object starting from one end, reaching the other end, and those two events take a time, delta X prime and delta T prime, and if the velocity relative to S prime is v1, we can write delta X prime is v1 delta T prime. Okay, so now let's plug those into the Lorentz transformation. So we have delta X, again, how much now this object has moved between the two events, starting here and ending up somewhere, according to the person standing outside in reference frame S. So that's going to be gamma, and we have to be careful what gamma that is. So that's gamma calculated with respect to V2, right? The relative velocities of the frames. And then I have delta X prime plus V2 again, that's relative velocity delta T prime. And delta T is going to be this gamma of V2, delta T prime plus V2 delta X prime over C squared. Okay, so I can stick that into this. So this becomes gamma V2. I have a delta T prime that I can factor out. And then I get V1 times, yeah, just V1, right? Delta X prime is V1 delta T prime, V1 plus V2, right? I'm factoring out that delta T prime. Here again, this gamma of V2, again, let me factor out the delta T prime, same thing. So I get 1, and then that delta X prime is V1 delta T prime. So when I factor out the delta T prime, I end up with V1 V2 over C squared. And now the velocity in frame S, let's call it W, is going to be just delta X over delta T, right? How much displacement I have over what time interval. So we see all the gammas and delta T primes just cancel out when I take the ratio. So we find omega, sorry, W, or whatever we want to call that velocity, is V1 plus V2 over 1 plus V1 V2 over C squared. So that's kind of nice. We see when the velocities are much smaller than C, this thing V1 V2 over C squared can be neglected. So we recover the Galilean result for the addition of velocities. We can see that, for example, if that V1 is c is something is moving with the speed of light. So consider v1 equals c. Object is light, or is a photon. What are we going to see? We will see w becomes c plus v2, whatever that v2 is, as long as, of course, it's less than c. Bad things happen if we put velocities larger than c into these equations, plus c v2 over c squared. So multiplying, let's say, both the numerator and denominator by c, I find fc, c plus v2. Here, c times 1 is c times that gives me a c squared. It cancels that, so c plus v2. These cancel out, so that's c. So regardless of the speed of the frame, of the relative speeds of the frame, we get the same velocity for light, which is, of course, the postulate. So if things are hanging together, that's what we expect here. We can also generalize this to the case where that velocity is not horizontal, is not in the same direction as the direction of the motion of the frame. So again, let's say we have S prime here that's moving with velocity v. And then let's say an object is moving in some direction. So it has a u x prime and a uy prime in the vertical direction, or in the transverse direction, to the direction of motion of the frame. So this is S. Now, if I want to find the vertical component of its velocity in frame S, I can again use Lorentz transformation. So ux, like the x component, it's the same formula that we just derived. It's going to be that ux prime plus v, 1 plus ux prime v over c squared. And if I want to find uy, so I have to consider the displacement in the y direction. So there's really no transformation in the direction perpendicular to the direction of the motion. So delta, let's say y is going to be delta y prime. And uy going to be just delta y divided by delta t, which becomes delta y prime divided by delta t. The expression for delta t is this gamma of v times delta t prime plus v delta x prime divided by c squared. So you see that if I divide both sides by delta t prime, what I get here is going to be delta y prime by delta t prime, which is this uy prime, the velocity in the S prime frame. And then I have this gamma that remains, and then I have 1 plus b delta x prime divided by delta t prime is going to be ux prime divided by c squared. So that's called the transverse velocity addition formula. Right, again, in the Galilean case, when v is much smaller than c, gamma goes to 1, right? That's vu prime x over c squared goes to 0. So the velocities in the vertical direction are going to be the same when we go back to the Newtonian physics. And the final result for today is so-called invariant intervals. So I kind of leave the derivation until later, but I just want to give like a preview of what that's all about. And let's forget about space-time and relativity a little bit. Just go back to vectors in space. So if you have some vector R, it has some components, right? So let's say you have some reference frame. Okay, so if it's x and y in some coordinate system, you will say, okay, so the x component is going to be this length here. The y component is going to be this length here. And the same object, right, the same vector, so let me draw that again, the same length, same direction. If I pick some other coordinate system, maybe x is pointing this way and y is pointing that way. So it's going to have like very different components. So let's say now in this coordinate system, let's call them x prime and y prime. It will have different components. So it gets transformed according to that, to some rotation, let's say r prime x, r prime y, which is in this case negative. But the length of this vector is the same. So there is a quantity that would be invariant, and that's a function of these coordinates. So we know rx squared plus ry squared does not change in that rotation transformation. So now events in relativity are like points, and actually we're looking at intervals between events. We're looking at delta x's and delta t's, right? So a vector r is really like again a displacement from one point to another point. So delta x, let's say, and also we can have delta y, delta z, and delta t. These things can be thought of like the component of some vector, right, in some space that also includes time, so-called space-time. And the Lorentz transformation essentially tells us when we move from one inertial frame to another, how do these components change? But there has to be something about that vector that's invariant under this transformation. And it turns out this is given by notation is delta squared. That can be written as c delta t squared minus delta x squared. You can also subtract delta y and delta z. So if we perform a Lorentz transformation on this quantity, we're going to get delta t prime, delta x prime, delta y prime, delta z prime. But that combination is something that's independent of the transformation. So that sort of gives the notion of length in space-time. All right, so I think that's a good place to stop. So next time, we'll spend some time proving this, and then depending on the sign of this invariant interval, we can have various cases, and there's a relationship to causality that we'll discuss. So yeah, that's a good place to stop.